Today we're going to be talking about areas and volumes of similar solids. And here we have two pyramids, Pyramid A and Pyramid B. And let's look at the ratios of the corresponding parts. So the altitudes of our pyramids, 8 to 20. Well, that's going to reduce to, if we reduce each by 4, we get 2 to 5. Now, are the rest of these corresponding parts in that same ratio? Well, let's look at that. 4 to 10. When I reduce that each by 2, that's also 2 to 5. And then our slant height, 10 to 25. When I reduce that each by 5, we also get 2 to 5. So all of our corresponding parts are going to be in proportion, and our scale factor, notice, is 2 to 5 because that's the same ratio. So therefore, our pyramids are similar. Now what I want you to do right now is I want you to pause the video and I want you to find the perimeter of the base, the lateral area of each one, and the volume of each one. Okay? And on the next slide, we're going to look at how the perimeter of the base, the lateral area, and the volume is going to compare to this scale factor that we found. So pause the video, find those on your own, and I will be looking for that when I check your notes. Okay, so hopefully you paused the video and you've done what I've asked, especially because I'm going to be looking for it in your notes. So, perimeter of the bases for Pyramid A. That was 16 because it's 4 times 4. Perimeter B, 10 times 4. So their ratio is 2 to 5. Notice that this is the scale factor that we found on the last slide. Now the lateral area, okay, perimeter of the base, 1/2 times the slant height, we get 80. For Pyramid A, Pyramid B, we get 500. We get 4 to 25. Hopefully you recognize, comparing that to our scale factor, that's our scale factor squared. Now looking at the volume, we get 128 over 3, 2000 over 3, and that ratio is 8 to 125, and hopefully you recognize that that is the scale factor to the third power. So when we had two similar solids, notice how perimeter of the bases, a one-dimensional, is exactly what the scale factor is. A two-dimensional, when we're looking at area, it's the square of the scale factor. When we're looking at three-dimensional volume, that is our scale factor cubed. So our conclusions then is the scale factor is A to B, the ratio of the corresponding perimeter is A to B. The ratio of the base areas, so lateral areas and surface areas, so any area feature is going to be the square of the scale factor, and the ratio of the volumes is the cube of the scale factor. Okay, so our first example. Diagonal of one cube is 2 centimeters. Diagonal of another cube is 4√3 centimeters. The larger cube has a volume of 64 centimeters. We need to find the volume of the smaller cube. Since all cubes are similar, I can look at the ratio of any of the corresponding parts. So let's look at the ratio of the diagonals to figure out what our scale factor is. So our scale factor is 4√3 to 2. When I reduce that, I get 2√3 to 1. Now to figure out what the ratio of the volumes are, okay, what I have to do is I have to take and I have to cube 2√3 over 1 and set that equal to the volume. The volume of the larger cube is 64. I'm trying to find the volume of the smaller cube. Let's do a little sidebar over here, what 2√3 cubed looks like. Well, that's 2 root 3 times by 2 root 3 times by 2 root 3. So I have 2 times 2 times 2. That's going to be 8. I have root 3 times root 3. That's 3 times by another root 3. So our total is 24 root 3 over 1 is equal to 64 over x. Cross multiply. Divide. Now up over here, I'm going to simplify 64 over 24. That simplifies to be 8 over 3 root 3. I can simplify those numbers, anything that's outside the radical. Now I need to rationalize the denominator. So therefore, the volume of our larger cube is 8 root 3 over 9, because 3 root 3 times, or root 3 times root 3 is 3, so I have 3 times 3, that gets me 9 in the bottom. So this is our value. Make sure you give me units. I almost forgot to put units on. Second example, two similar cones have volumes of 12 pi and 96 pi. The lateral area of the smaller cone is 15 pi. What is the lateral area of the larger cone? So we have the ratio of our volumes. So find 12 pi to 96. This is the ratio of the volumes. When I go ahead and I reduce that, I get 1 to 8. So our scale factor cubed is 1 to 8. So then I cube root, and our scale factor ends up being 1 to 2. So the ratio of the lateral areas is the scale factor squared. So I square the scale factor is 1/4. That equals the lateral area of the smaller cone is 15 pi. I need to find the lateral area of the larger one. When I cross multiply, I get 60 pi. Now look and see, I don't have any units, so I don't need to worry about units. Okay, our next example, and this is based off of examples that you're going to find in your homework. So when you ask me about this question in class, I'm going to say make sure you look at your notes. So make sure you're paying attention to this. Two similar cones have radii R1 and R2 and height 1 and height 2. So let's call this pyramid 1, pyramid 2. So the volume of pyramid 1, not pyramid, I'm sorry, cones. Cones, 1/3 pi R1 squared times by H1. The volume of pyramid 2 is 1/3 pi R squared, R2 squared times the height, H2. I'm trying to prove the ratio of the volumes is H1 cubed to H2 cubed. So let's look at the volume of 1 divided by the volume of 2. So the volume of 1 is 1/3 pi R1 squared H1 divided by the volume of pyramid 2, which is 1/3 pi R2 squared H2. Now look at what can cancel. Now let's look at this. Okay, remember these two pyramids, not pyramids, cones, Marnell. I don't know why you put pyramids there. Cones. I don't know what I'm thinking. I'm recording this kind of early in the morning. That's probably what I'm thinking. These two cones, okay, are similar. So their scale factor is the ratio of corresponding parts. So their scale factor is H1 to H2 or R1 to R2. These two scale factors are the same since our cones, since the cones are similar. So what I can look at is I can look at these ratios of the radii, and I can say that that's equal to H1 over H2 because the corresponding parts are going to be equal in terms of their proportion. So those radii become H1 over H2, and then I have another H1 over H2, so therefore I have H1 over H2 all to the third power. Or you could look at that as H1 cubed to H2 cubed. So again, I used the idea for my cone. I looked at the volumes. I recognized that the scale factor is the ratio of any of the corresponding parts, and that scale factor is going to be the same for any of the corresponding parts. And I substituted in to my volume equation. Okay, there are your lesson questions. Please make sure those are submitted on time.